I mainly work. I mainly work with LC-MS devices, and in particular in the context of metabolomics analysis, because these strategies are very suitable for detecting food fraud. And I will start this presentation with a short introduction concerning food fraud and metabolomics, and then I would like to present two of my projects. The first project is about developing an analytical method for determining the geographical origin of asparagus, and the second project aimed to distinguish between different truffle varieties. So the major food fraud questions concern the biological and chemical identity, and this means the change of species or varieties and the chemical composition, because some raw materials are simply cheaper than others. And furthermore, the labeling information regarding the geographical origin is changed, for example, to evade taxes or to pretend a higher quality. And in addition, there are false statements about the production process that may relate to the use of genetic engineering or whether a product was produced organically or conventionally. Food fraud is often done for financial reasons, but sometimes such practices can also result in real health problems, for example, if allergenic substitutes are used. So what counter strategies do we have? One possibility is to document every single step, but documents can easily be created or changed. Another option is to carry out visual or sensory examinations, but this requires special trained experts, and often such methods are not sensitive enough. And other options can be the use of tracking or tracing technologies, for example, by means of blockchain, but here two changes can be made directly to the product. So analytical methods can be a further solution because they are independent of external information and therefore they are very safe, but sometimes they can be very expensive. And in addition, some of these methods have yet to be developed because food counterfeiters can be very creative and always come up with new ways to achieve the greatest possible financial gain. And I think most of you are probably are quite familiar with the term metabolomics. Nevertheless, once briefly, as a repetition for everyone, metabolomics means the totality of all metabolic products in an organism. These may be, for example, sugars, amino acids, or lipids. And sometimes metabolites are also called small molecules because they usually have a molecular weight of 80 to 1,500 Daltons. And according to estimates, there are around 200,000 metabolites in the entire plant kingdom. And of these metabolites, it is only possible to analyze a small fraction because at the moment there are not so many analyzers which can be used for such scientific issues. And normally these experiments are carried out by MS or NMR devices. The big advantage of a metabolome analysis is that the qualitative and quantitative presence of metabolites in an organism can be influenced by many different factors. And these factors can be used by us to solve different scientific questions by recording molecular metabolite profiles. So as I've already briefly indicated at the beginning of my talk, I choose asparagus as the first example for this presentation because asparagus is a very special food, but mainly for the German people, and it is the most commonly grown vegetable in open land in Germany. The most German consumers prefer asparagus from certain growing regions, and there are many reasons for this behavior, partly because of the taste, but also sometimes because of shorter transport routes or simply out of conviction. And these requirements lead to high price differences depending on the cultivation area and the assumption that more German asparagus is sold than cultivated. So therefore, misleading labeling regarding the geographical origin is suspected. And at the moment, there is no reliable method to determine the geographical origin of asparagus. The state authorities use isotope ratio mass spectrometry, but sometimes the results are a little bit uncertain. And that was the reason it was up to me to develop an alternative method. And when developing such method, it is quite important that authentic reference material is used because the whole analysis is based on these samples. And we solved this problem by driving with such a transporter with which the samples can be cooled across Germany and also Poland and the Netherlands, and picked up the samples directly from the producers. And additional samples from Greece, Spain, and Peru were bought with the help of importers because, yes, of course, these countries were a little bit too far away from us to collect the samples by ourselves. So the samples were taken over several years so that climatic effects could also be considered. And at the end of this project, we had about 500 samples in total. When it was possible, we also wrote down some metadata, for example, which pesticides or varieties were used, because such factors can also have an influence on the results. And back in Hamburg, the samples were washed, ground, freeze-dried, and stored at -80 degrees. So in this way, changes of the metabolites should be avoided as far as possible. And subsequently, the asparagus powder that I obtained was measured using an UHPLC, which was coupled to an electrospray ionization quadrupole time of flight mass spectrometer. And I used various methods to record as many metabolites as possible, simply to increase the probability of detecting the best marker substances. And this strategy is also called a non-targeted approach. So one method focused more on polar metabolites and the other focused more on non-polar metabolites. And the difference between these methods was the extraction process and the column that I used for the UHPLC and the chromatographic separation. And in addition, all the samples were measured in positive and negative ionization mode. On this slide, you can see two chromatograms that I obtained from my LCMS measurements. And yes, at a first glance, these figures might look a little bit confusing, but they are not really complicated. Because here on the x-axis, you can see the chromatographic separation that I obtained by the UHPLC. And on the y-axis, you can see the mass to charge ratio, which was provided by the mass spectrometer. And every single dot in this chromatogram represents one feature. And the more intensive the colors, the higher the concentration of such a feature. And in total, I was able to detect about 5,000 features in one sample. These were both polar metabolites, which one would expect in asparagus, for example, some sugars or amino acids, but I could also record many lipids. And in principle, the fat content of asparagus is not very high, but it is still sufficient to be able to detect such metabolites. So for example, I could detect triglycerides or different phospholipids. And for the next step, I could look in every single sample and for each single compound if there are differences of the signal intensities. But this can be quite time consuming, and that is the reason why I use different multivariate methods for my data evaluation. And such a data analysis is shown here on this plot, because in this plot, each dot represents one sample, and points that are close together are chemically similar, and that means in our case that they have a similar geographical origin. And all the samples from Germany are marked in red, and all the samples from abroad are shown in green. And yes, I think it becomes quite clear that a good separation could be achieved. In the next step, I looked which signals were responsible for this distinction, and I identified them using MS pigment spectra. And here a very small selection is shown, but there are also much more compounds that show a dependency on the geographical origin. So for example, I was able to identify oleic acid or various phytosterols. And these phytosterols were quite interesting because it seems to depend on the glycosylation pattern, whether the compounds are present in higher concentrations in the samples from Germany or in higher concentrations in the samples from abroad. And almost all of the relevant marker compounds could be associated with different types of plant stress. In principle, time of flight analyses are great for such approaches, but they have also some disadvantage. And one big disadvantage is the low reproducibility. Because MS analyses are quite sensitive to temperature fluctuations, vibrations, and contaminations. So as a result, measurements that were carried out at longer time intervals cannot be directly compared with one another, and the transfer to other devices is not very easy. And what that looks like can be seen on this plot here, because here I've carried out 3 series of measurements, each with the 1 year time interval. So the first batch was measured in 2016, the second batch was measured in 2017, and the last batch was measured in 2018. And the measurement differences are very large, and they are so large that they hide the variances of the samples. So there are several ways to deal with this problem. And we decided to look for signals that occur constantly in the samples and are not subjected to any changes. And we designed this metabolites, housekeeping metabolites, and used them to normalize the data by simply calculating the ratios. And in this way, the focus was no longer on difference based on the time of measurements, but on differences based on the geographical origin. And what this looked like is shown here, because here I have selected an example metabolite, and the geographical origin of the samples, which came from Germany, Poland, the Netherlands, Greece, and Peru, is plotted against the signal intensities here on the second axis. And at the first glance, you cannot see big differences between the concentration concerning the signal intensities and the geographical origin. But after the normalization step with the housekeeping metabolite, it becomes quite clear that the substance is present in higher concentrations in the samples of Greece and Peru. So this procedure makes it possible to catch up on individual measurements at a later point in time. There is another disadvantage with time of flight instruments, besides their reproducibility, because these devices are quite expensive and also maintenance intensive. And therefore, such high resolution MS analyzers are hardly represented in routine laboratories. And for this reason, I developed a simple targeted method for the best 20 marker compounds. And here I used a Q-trap mass spectrometer device, and these devices are much more robust and smaller, and they are available in every normal equipped food laboratory. So these devices are not suitable for screening approaches, and the marker, that means that the marker compounds must be known. And in addition, a quantification must be carried out by means of an external calibration to ensure that the comparability of the samples is given. The difference in the concentration of these 20 marker compounds can be used to create such spider plots. And depending on the country, there's a specific pattern that can be used to determine the geographical origin. And in this way, it is possible to transfer the non-targeted methods, for which I used the high-resolution mass spectrometer, to routine analysis. And the second project that I want to share with you was a very large project with many further partners, and we called this project Food Profiling. And this project was done on truffles and walnuts, but I will only go into the truffle analysis in the following part. And here the sampling was taken over by a specialized company that has been trading in truffles for many years. And the company's employees traveled to the harvesting countries, accompanied the truffle sampling, and sent us the samples to Hamburg. And in Hamburg, I prepared the samples for the other project partners and sent them aliquots, because these samples were also analyzed by further scientific institutes using various omic technologies. These included genomics, proteomics, metabolomics, that was my part, and isotopolomics. And the data evaluation was taken over by the University of Tübingen in order to be able to estimate which method is the most promising. And in addition, this project was accompanied by several industrial partners in order to later establish these methods in routine analysis. So in case of truffles, the commercial price is mainly determined by the species, and special truffle species can cost several thousand euros per kilo, while the cheaper truffle species cost only a tenth. And a visual distinction is often not possible, or it needs a lot of experience. And for this reason, I also analyzed the samples with an LC-MS instrument, and this was also a QTOF instrument, but this instrument was additionally equipped with an ion mobility cell. There are different ion mobility cells, but here I used a drift tube. And in this drift tube, the analytes are conducted through the cell by means of an electric constant field. And in addition, the cell contains nitrogen molecules, and the analyte ions collide with the nitrogen molecules. And smaller molecules collide less frequently with the nitrogen and can cross the drift tube faster than bigger molecules. And in this way, an additional separation of the ions according to the charge, the size, and the shape is obtained. And by measuring the drift time that the ions need to cross the tube, a further parameter can be calculated, and this parameter is called CCS value. CCS stands for collision cross-section, and this parameter can be used for additional identification. And this slide shows an example chromatogram, and it's quite the same with asparagus, because I was also able to detect very different lipids. These include, for example, various phospholipids or glycerolipids and ceramides, and also some sterols. And here on the figure on the right, you can see the corresponding CCS values together with the retention time from the UHPLC separation and the mass to charge ratio. So the implementation of the ion mobility cell can further increase the metabolite coverage, because we have an additional separation level with which also isobaric compounds can be distinguished from one another. The classification of the white truffle samples, especially the species Tuber magnatum and Tuber borchi, worked very well. And I was also able to detect a whole range of different marker metabolites. So some of the most relevant marker metabolites are presented here, and compounds that are shown in red are present in higher concentrations, and compounds that are shown in blue, lower concentrations. And what you can see here on this plot is that just a few marker compounds are enough to distinguish between the different truffle species, and it should also be possible to develop a simple targeted method with a smaller MS instrument. The differentiation of the black truffle species, Tuber melanosporum, Tuber indicum, and Tuber aestivum, was similarly easy to perform, but I could not identify so much marker compounds, which is mainly due to the fact that the structure of many compounds is not yet known, but I think that will certainly change in the next few years. Nevertheless, also a few marker compounds are sufficient to distinguish between the different species too. And with this results, I would like to end my presentation and thank my partners and you for your attention.
Markus,